This preview is for evaluation only and cannot be used for public screening.
It's been a long time since we last saw each other.
Yes, seems like ages. All that time we spent working on our A-levels before we went to university. Didn't you get an A in physics back then?
And even in maths. You remember how you always copied my answers, don't you?
Only once or twice. I was never really big on maths.
What was our maths teacher's name again?
Grimsdale, as I recall.
Yeah, that's it, Grimmy. We sat in maths class and you kept asking, why are we learning all this stuff? What is the point of all this? All these formulas and calculations.
You're right. I never really understood any of it.
But then you decided to do something different.
You're right. I went abroad and made my career, while you chose something a lot simpler.
That's true, I really did. I studied physics. It was great.
You little Einstein.
Yes, mostly it was astrophysics that I went for. The universe, the vast expanses. Crazy, isn't it? Just imagine, all the stars that you see in the sky belong to the Milky Way, our home galaxy. No matter which way you look, all of them. But back when I was studying, nobody really knew how far away these stars really were.
Really? I thought scientists already knew everything there was to know about them.
No, that was just what they were trying to find out. That was my first job. That was the summer of '89, remember?
Of course. The demonstrations in Beijing, free elections in Moscow, and the fall of the Berlin Wall. The whole world was topsy-turvy back then. A crazy time. I was always on the road somewhere.
And we were sitting in South America at the European spaceport in Kourou. That's where we were launching the Ariane rockets. And our satellite was ready to launch. It was called Hipparchos, named after the famous mathematician Hipparchus of Nicaea.
I've been to Kourou once, as a member of a delegation. Not much of a place for a summer vacation.
Even less so back then. Preparations were totally frantic. But finally, we got started.
10, 9, 8, 7, 6, 5, 4, 3, 2, 1, top.
Dead silence. The software had aborted the launch. We had 1 hour left to fix it. And then...
4, 3, 2, 1, mise au feu.
Liftoff. Our satellite was in space. I can't tell you how relieved we were.
You guys were lucky.
Well, that's what we thought too, but first we had to get our satellite into a higher orbit before we could activate it. And that meant igniting the apogee boost motor. And that all went wrong.
What happened?
The ESA control center sent the ignition signal, but the motor didn't fire. Not even after the second, third and further attempts. We had no idea what the problem was. We were devastated.
Terrible. All that work for nothing.
Were we about to give up? No way. We had to find a solution. And some of the brilliant minds at ESA finally came up with one.
Gentlemen,
This
what can we
preview
do?
is for
We can
evaluation
reprogram the
only
attitude
and
thrusters
cannot
and
be
try to
used
gain
for
altitude.
public screening.
Oh la la, that has never been tried. I don't think they will hold up.
It is risky, but I don't see any other alternative.
We'll never reach the planned orbit.
Yes, but the main thing is to bump up the altitude before the satellite is burned up.
All right, gentlemen. This sort of maneuver has never been attempted. But let's try. To your stations.
Did you finally make it?
Yes. These tiny attitude thrusters edged the satellite up higher and higher. It was not the best solution, but at the end of the day we had a mission. We were able to take measurements. With me so far?
Of course. But what were you measuring?
We were taking new 3D measurements of the Milky Way, the distances to the stars. You know, plotting the stars isn't as easy as it might sound. We can't just hold up a measuring stick. So we had to use a few tricks and mathematics.
Please, spare me the mathematics.
Just a bit, but then I will open this box of chocolates.
Sounds like something Grimmy should have said. Maybe I would have paid more attention.
So listen, we used the so-called parallax measurement, basically a simple triangulation.
Would you open the chocolates already?
Patience, patience. Hold your thumb up in front of your nose at the end of your outstretched arm, up there, pointing at the crosshairs. Excellent. Now look at your thumb with just one eye. Just one eye, close the other one. Now move your head to the left and right. Slightly, like that, left and right. What do you see?
Well, my thumb is moving back and forth against the stars.
Now you see, that is exactly how we measure the distance to the stars. Your head is our satellite, your thumb is the nearby star, and the stars in the background are the ones that we aren't even trying to measure because they're too far away. That's the trick. And using basic mathematics, we can simply measure the distance. It is A divided by the tangent of alpha.
A divided by the tangent of alpha. Now you're really in your element.
Yes, this is simple trigonometry. You could just as well say this is the theorem of Hipparchus. The line A is the wiggling of your head, and alpha is the angle to your thumb. Got it?
To tell the truth, it's all Greek to me.
Then let me show you something else. Oh, by the way, the chocolate.
Good choice.
Okay, imagine you're sitting in a train and looking out the window. You see a village with a church tower and mountains behind it. While you're moving, the church tower seems to move against the backdrop of the mountains, which are a lot farther away. That is exactly what parallax is, the thing we are measuring. The angle to the church tower. Got it?
So how am I supposed to measure the angle to the church tower? And from a moving train?
Bravo! You just figured out the crux of the matter. The real problem is finding the angle. Can be measured, it is just a matter of how precisely. The angle of the church tower is easy to see, but the angle to the stars is so minuscule that the ancient mathematicians simply couldn't measure it. Hipparchus tried to measure the distance to the sun using parallax, but even couldn't manage that, let alone measure the parallax of other stars.
And then?
They turned logic on its head and said, because we cannot measure the parallax of any stars, they all must be the same distance away, and some are just brighter and some dimmer than others, as if they were all fixed to the vault of a great celestial dome. 2,000 years ago, before we were able to measure distances, that all made sense.
An odd concept. But yes, common sense is far from proof. How can we understand anything we can't measure?
Now you see, measurement is knowledge. Nowadays we understand that, but imagine a time when no one had any idea. And imagine all those stars every night. You ask yourself, what are they? Why are they there?
I once read something very interesting. You must have heard about the cave paintings in Lascaux in France.
This preview
Among
is
these
for
marvelous
evaluation
early
only
paintings,
and
they're
cannot
said
be
to have
used for
discovered the
public
oldest
screening.
known pictures of the stars. Just imagine, they drew this stuff back in the Stone Age. And in the midst of all these wild animals is a puzzling figure. A bird man, a bird on a stick, and a bull. And the location of their eyes lines up exactly with 3 of the brightest stars in the night sky. Crazy, isn't it?
Yeah, that's the summer triangle made up of Altair, Deneb and Vega. That's no coincidence, since Vega, the eye of the bull in the cave, was the North Star back then, and the Birdman could well have been the first constellation.
I love these drawings. Another spot shows a primeval bull, an aurochs, on the cave ceiling. What a work of art. And up there, above his back, are 6 tiny points. They're thought to be stars, too.
Yes, my friend, these are the Pleiades, a cluster of stars that appeared back then in the winter and was visible all night long during spring. Do you know what that means?
Certainly. The Pleiades heralded the return of spring. So these stars were a sort of calendar.
Exactly. The stars were the only calendars they had, and later, when people became settled, they sowed their crops, harvested and feasted according to the stars. In ancient Egypt, the stars were vital to their survival. Every year when the star Sirius appeared, the Nile also flooded. Those who were aware of that did not drown. It was just that simple. The Egyptians had names for more than 100 stars. That's what an early star chart looked like. This large ceiling fresco comes from the tomb of Senenmut.
Amazing what they knew back then.
Of course. In ancient China, they also read the stars. Chinese imperial court astrologers were said to have named some 400 stars. They tried to establish a connection between the celestial order and the emperor's actions.
Stars and politics. Sounds like hocus pocus to me.
As well it is, but people have always seen the stars as a guiding light, a fixed order. Astronomy and astrology were intermingled, and later for the Babylonians, the ones who gave us our present constellations.
Do those include the 12 signs of the zodiac?
Yes, back then the year was divided into these 12 constellations. Later they heaped all sorts of things on top of them, and nowadays horoscopes and the science of astronomy have nothing at all to do with each other. And then came Alexander the Great.
Ah, the Battle of Issus was most vicious.
Right. Alexander conquered the Babylonians and brought their knowledge of the stars to ancient Greece, and their myths too. The fables and stories of the figures in the night sky. The Greek mathematician Eratosthenes compiled all of them.
A mathematician again.
Yes, but many of these myths are familiar to you as well. And one of them is my personal favorite, the origin of the Milky Way. Listen. About the Milky Way. It was named Galaxis because none of Zeus's sons were allowed to share the honor of the heavens if they did not drink from Hera's breast as babies. That is why young Heracles, an illegitimate son of Zeus, was taken after he was born and laid at the breast of the sleeping Hera. and young Heracles suckled so hard that Hera noticed the ruse and pushed him away, spilling her milk,
This preview
which
is
gave
for
rise to the Milky
evaluation
Way.
only and cannot
What an
be
image.
used for public screening.
Every culture in the world has a story about the Milky Way, because it's always been there. To the Babylonians, it was a giant serpent. To the Australian Aborigines, a water monster. To the Aztecs, it was the smoke arising from an enormous fire. And in India, it was the sacred path of the devout.
In fact, nobody had any idea what the Milky Way really was. Even when old Hipparchus drew the first big star chart, he didn't know. That's why he just left the Milky Way off it.
What's a lot of spilt milk doing up there anyway?
Yes, precisely. But to make it even worse, Hipparchus had no idea even what stars really were. He simply drew them as dots, just as he saw them, 1,000 dots.
And what became of his star chart?
It remained the state of the art for 1,000 years and was further refined. In the Islamic world, for example, the stars were drawn as figures, and more stars were given names, Arabic names. The two twins in the constellation of Gemini, shown here in female form, are made up of the stars Wasat, Mabsuta, Al-Zir, and Al-Hana, and Al-Ras al-Tum al-Mukhadim, and Al-Ras al-Tuam al-Mu'akab. Arabic sounding enough for you? Still today, the sky is full of names like that.
Persia and the Middle East, they were leading in science back then. While things were pretty dim in Europe in those days. I mean, it was a rather dark age for science.
Yes, the Dark Ages. The works of the ancients were kept out of sight. But that changed quickly when people discovered how important the stars were for navigation, especially at sea. They started building improved instruments for measuring angles, the Jacob's staff or the mural quadrant. The stars became key to navigation. Astronomy was all the rage again. New charts were created everywhere, like the German astronomer Johann Bayer, who created a celestial atlas with 50 individual charts. That was as precise as they could get with the naked eye.
Until Galileo Galilei invented the telescope.
Indeed. Well, he didn't invent it, but he was the first to turn the telescopio toward the night skies in 1609. That was a real breakthrough. Mind-blowing. Galilei was the first to see that the Milky Way was not a cloud, not Hera's milk, or a water snake, but a belt made up of countless stars, millions of stars. And he saw the moons of Jupiter orbiting the giant planet.
That must have knocked his socks off.
I'm sure it did. And it was a giant leap forward, the dawn of the age of science, and finally the end of the geocentric view of the world.
A revolution. The Earth was no longer the center of everything. But nobody wanted to believe that.
No, but it was no longer a matter of belief. It was something that could be proven. His observations backed brand new theories saying that the Earth was circling the Sun. And then something interesting happened. With ever larger telescopes, the list of known stars grew longer and longer, and when it got to around 20,000 stars, the astronomer William Herschel wrote, "The stars that we see are the whole universe, and our sun is at its center."
Crazy. The same mistake as 1,000 years earlier. We always have to be in the center, with everything revolving around us.
Yeah, the same mistake. But Herschel had no way of knowing otherwise, because he had no idea how far away the stars really are. It took decades until they could finally apply what old Hipparchus had already calculated long before. The first stellar parallax wasn't measured until 1838.
What exactly was that again?
The angle you use to calculate distances, the triangle.
Oh yes, the tangent of something or other.
It took Friedrich Wilhelm Bessel
This
almost 2
preview
years
is for
to take that single
evaluation
measurement.
only and
But
cannot
that
be
was
used
the
for
turning
public
point.
screening.
Finally, it could be proven that the stars are not affixed to the vault of the heavens, but are located at different distances from the Earth, and that they themselves are suns, individual suns in a vast universe. Come on outside. I want to show you something. There are only a few dozen stars visible here in the city because it's just too bright.
Yes, this damn light pollution. Up in the mountains, the entire sky is strewn with stars.
Up there you can recognize a few thousand stars with the naked eye. Look at that star over there, just above the horizon. That's Sirius, the sacred star of ancient Egypt. Let's fly there. In our minds, of course. And I'll show you what it means to know the third dimension, that of distance.
Go for it. I'm buckled up.
Sirius is the brightest star in the night sky. Together with Rigel, Procyon, Aldebaran, Pollux and Capella, it forms a hexagon, the winter hexagon. People used to think they were equidistant. They were completely wrong. Assuming that we could travel at the speed of light, then it would take just 1 second to reach the Moon, a couple of minutes to Mars, and a couple of hours to get to Pluto at the edge of our solar system. Behind that, there's a region of ice chunks and then practically nothing, a vacuum. 8 years of nothing, until we reach Sirius. Sirius is only twice as big as the Sun, but it burns a lot hotter, almost white, and it's burning up faster. It is accompanied by a small white dwarf, but that star is not visible from the Earth with the naked eye. It's just another 3 light years to Procyon, almost a double star, 2 unequal partners who cannot get away from each other. After 30 years of travelling, we get to Pollux, in the constellation Gemini, a star that has at least 1 planet orbiting it. Beyond it is Capella, the tip of the hexagon. 2 large, hot stars circling each other in close orbit. They are so close to the end that they have blown up to giants. "70 light years from Earth, we reach Aldebaran, a red giant entering into the last phase of its life. While it is slowly running out of fuel, it will start swelling up and losing its matter into space, a process that takes millions of years. Everything has its own pace in the universe. We've already covered 100 light years, 200, 400, then we come to the Pleiades, the calendar stars of the cave dwellers and the Egyptians, a few bright stars in a cluster of more than 1,000 stars. They were all formed together, and they are still wandering together through the Milky Way system. All stars are moving constantly, even our Sun.
This preview is for evaluation only and cannot be used for public screening.
Veils of thin gas, helium, hydrogen, they're all drawn out into fine trails in which hundreds of thousands of stars glow. Here is the sixth star of the hexagon, Rigel, a blue giant, 1,000 light-years away and 100,000 times brighter than the Sun. How long it took us to understand that distant objects can be so enormous. The interstellar gas grows thicker and it is joined by dust, fine particles microscopically small, but making up a huge mass altogether. The smoke from gigantic explosions in space. Pressure waves compress the gas and dust so densely that they form nebulae and dark veils. These enormous opaque clouds are the birthplaces of stars. This is where new stars are being born out of gas and dust, star by star, sun by sun, each of them different, most of them with planets. Newborn stars blast off all the gas and dust surrounding them, ready to form new stars one day. An endless recycling process of matter, just like our own sun was created a long time ago. A giant star much larger than our sun explodes as a supernova. Its core collapses, and from the ashes of its shell, the process of star formation begins anew. As the interstellar gas and dust get more compressed, nebulous arms and giant tentacles form. These are the spiral arms of the Milky Way, our own home galaxy. A wafer-thin disk made of gas, dust, and billions of suns, and our own sun is just one of them. There is a glow on the horizon. It points the way to the heart of the Milky Way, hidden behind black dust clouds of matter.
This preview is for evaluation only and cannot be used for public screening.
The center of our Milky Way is dominated by extremes. Millions of stars are circling a small black spot at mind-boggling pace. Here is the black hole at the center of our galaxy, a mysterious place with such a powerful pull that not even light can escape. That is our Milky Way in all its glory, with its spiral arms made of stars, gas and dust. Together with all the other stars, our solar system follows the eternal spin of one of the spiral arms too. We are slowly and endlessly orbiting the center of the Milky Way. We humans, our Earth, are all a part of the Milky Way. Our sun is one of a billion suns. And since we're sitting in a region halfway from the center, we see the Milky Way as a narrow, glittering band across the night sky. There are billions of galaxies in the universe. They are all moving through space, bound together by the mysterious force of gravity. Where does this gravitational force come from that holds billions of stars within a galaxy? The black hole at its center is not enough in any case. The mass of all the stars circling it, even their mass is not enough for a large attraction. The stars in the outer areas of the Milky Way are actually moving way too fast. According to the laws of physics, they should have spun off already. There has to be something, an unknown invisible mass that produces the missing force and holds everything together. Matter that we know nothing about other than it must exist. Dark matter. It must be even more powerful than the black hole. Dark matter is uncanny stuff. It is everywhere. It makes up 85% of all known matter, but we cannot see it, and we have no idea what it is. We tried to identify dark matter for many years, but frankly speaking, until now we don't have much idea of what it is. It remains one of the greatest unsolved mysteries of the universe.
I am most impressed, my dear friend. I've always thought you must have spent all your time in the corner of a physics lab.
Oh, not at all. I was always trying to solve the great riddles of the universe. Dark matter, for example. Or the question, how many planets are there in our galaxy? Or a problem that really affects everyone. Are there asteroids on a collision course with the Earth?
Yes, that seems to be a real problem. One that people have always underestimated, that comets and asteroids might threaten the Earth.
Really, and a lot of those objects are still unidentified. What good is it if we don't discover them until the last minute? We
This
need much
preview
more
is
precise
for
measurements if we
evaluation
want to be
only
able to make
and
reasonable
cannot be
predictions.
used for public
But
screening.
that should be no trouble with modern technology, shouldn't it?
Of course. As soon as our Hipparchus mission ended 20 years ago, we started the next one. And this one pushes up against the very limits of what technology can accomplish. Gaia is its name, our new satellite.
I knew you had an ace up your sleeve.
Gaia will, for instance, discover thousands of asteroids and deliver us the precision we need for collision warnings. But its main purpose is to draw a new three-dimensional map of the Milky Way. Gaia will help us find out more about the origins of our home galaxy. Right now, there are all sorts of theories out there because the measurements are so imprecise. But Gaia can measure the paths of the stars so precisely that we'll be able to retrace where the stars in our galaxy came from and where they're heading in the future.
You mean a sort of archaeology of the Milky Way?
Exactly. But for that, we needed a whole new approach. Gaia is a 3 by 3 meter cylinder with a solar panel underneath. Inside the body, there is a super rigid structure made of silicon carbide with no moving parts, everything designed at extreme precision. And right in the heart of the spacecraft, we have a gigapixel chip, 106 chips in fact, photosensors like in a digital camera, just much bigger. It's connected to 10 ultra-high precision, polished telescopic mirrors. That is technology at its very best. Tailor-made by the European Space Agency and the best industry laboratories all over Europe. Over 1,000 people have worked on it for years. Gaia is so precise that it can measure from 1 meter away how much your hair has grown in a fraction of a second. And this precision will allow us to measure quite precisely the positions, movements, distances, brightnesses and colors of 1 billion stars. 1 billion stars, just imagine that.
1 billion stars. Hard to imagine. And that people are able to build something like that. Incredible.
Unlike earlier times, we don't define a fixed background. You remember the story with the fixed stars behind your thumb?
Yes. But what is your point of reference?
We treat all stars as reference points. We measure the parallaxes, the angles in the triangle, individually for every single star, and we work out all the references and motions together. Finally, we are computing the positions, motions and distances for every individual star using mile-long calculations, a calculation with 700 million variables. That is leaps and bounds beyond anything we have right now. Every day, our supercomputers calculate billions of triangulations. I can see you wince at that thought. On top, our data have to be corrected billions of times over with the positioning data from the satellite and other error factors. 1,000 billion shots, enough to give even the most powerful computers a nervous breakdown. That is a Herculean task that takes years.
For which I do not envy you.
Not to worry, it's spread all over Europe. Hundreds of scientists are working on it. Enormous computer clusters.
And what do you expect to wind up with?
You won't believe it. In the year 2020, we're coming out with a table containing 1 billion lines and several hundred volumes, like a gigantic Excel spreadsheet.
Nothing but a spreadsheet? You must be joking.
No, that is really what we're doing. On paper, it would fill up 2 million ring binders. Anyway, we're putting together a brand new database of the Milky Way. And these columns of super precise figures will be used by astronomers all over the world to discover new objects and develop new theories.
Such as?
Oh, there's a whole series of them. The asteroids and supernovas I've already mentioned. We also believe that the Milky Way dates back to the very beginning of the universe, but we don't know where all the stars come from. With Gaia, we'll be able to retrace the movements of the stars, filter out the movement of outside stars, and finally come to fully understand the history of the Milky Way and its future.
This preview is for evaluation only and cannot be used for public screening.
And on top of that, we plan on discovering tens of thousands of planets, because one thing is clear, there must be countless planets in the Milky Way that resemble Earth.
So you're truly searching for extraterrestrial life?
Oh, of course we dream of finding life, but with Gaia we're simply laying the foundation for the real discoveries in the future. Like I said, measurement is knowledge.
Measurement is knowledge. I didn't know what physics is really capable of. Consider old Hipparchus with his star map. Who would have thought that this could teach us so much? Know what? In my next incarnation, I will pay more attention in maths class.
Yeah, that's a good idea. Looks as if we got everything right.
And a new adventure is about to begin.
This preview is for evaluation only.